Let us talk about the different important points related to the electrochemistry. First of all, let us revise the formulae which we required for the resistance and conductance for calculations. First of all, resistance is equals to the resistivity multiplied by L into A. Exactly opposite formula you will get for the conductance. So in case of the conductance, that is G will be equals to, that's your conductivity, that's K, multiplied by A upon L. So we can say this formula is nothing but conductivity if you calculate. So the K is equals to G into L upon A. Now while doing the calculations, we have to remember the conductivity K is generally, this is called as the cell constant B, and G is nothing but inversely proportional to the resistance. This formula is very important when I am talking about the MCQ point of view while calculations. Now in case of molar conductivity will be equals to, that's K into 1000 upon concentration. That may be expressed in molarity. Cauchy's law, the limiting molar conductivity of electrolyte, it's the sum of the limiting ionic conductivities. So molar conductivity, that's highest 0, that's equals to the contribution which is given by the cations plus the contribution given by the anions, because each contribution is independent of each other. In case of application of Cauchy's law, remember we use this for calculating the molar conductivities for any electrolyte at the zero concentration. Especially for the weak electrolyte, we use this. We can relate this conductivities, molar conductivities, with the degree of dissociation. Alpha is equals to molar conductivity divided by maximum molar conductivity. Also, the K, that is dissociation constant, is equal to molar conductivity square into C divided by molar conductivity 0 into molar conductivity 0 minus molar conductivity. So these are some formulas that we need for solving the MCQ related to the electrochemistry. Electrolytic cell, the conversion of the electrical energy into the chemical energy. So remember here the cathode will be negatively charged where the reduction will occur, and anode will be positively charged. Here we can have the electrical energy, different examples where actually we just allowed the reaction such as non-spontaneous reaction by passing some electrical current through this. So some of the products we can remember, if I take a molten NaCl, so what I'll get at the cathode and what I'll get at the anode. So if I talk about molten NaCl, I'll get the sodium and the chlorine gas at respectively anode. Instead of this, if I take aqueous NaCl, then I'll get hydrogen gas at the cathode and the chlorine gas at the anode. If I take molten NaOH, so here I'll get sodium at the cathode and oxygen at the anode. But if I'll take aqueous NaOH, then I'll get a hydrogen at the cathode and oxygen at the anode. One of the important examples, just remember aqueous H2SO4, where you will get hydrogen gas at the cathode and oxygen gas at the anode. In case of voltaic cell, where the conversion of chemical energy into electrical energy, where some spontaneous reaction occurs of its own so as to give the product. Here, remember, the cathode is positive and the anode is negative. Now, the particular examples like Daniell cell you can remember. Then salt bridge, connecting the two solutions to avoid the direct contact of the electrolytes and maintain electrical neutrality. Also minimize the liquid junction potentials. Now next important part for the MCQ point of view, that's a Faraday's law of electrolysis. The first statement, the first law, that's the amount of the given product liberated at the electrode during the electrolysis is directly proportional to the quantity of electricity passed. So we generally write this as amount of substance which is deposited is directly proportional to Q. So M is equals to Z into Q, where Z is a electrochemical equivalence. So finally we have Z, M is equals to Z, Q is I into T. So this is a formula we can use. for calculation. Now in case of the second law, when the same electricity is passed through the solution of the different electrolytes, the amount of substances liberated at the electrode are directly proportional to their chemical equivalence. So M1 is directly proportional to E1 and M2 is directly proportional to E2. Therefore, we can say M1 upon M2, that is masses deposited at the electrodes, is equals to the E1 upon E2. So these are the two formulas that we have to remember. Also here just remember the Z is nothing but the electrochemical equivalence, which can be calculated by using the formula E upon 96,500. So that's formula for the Z. Next part is a classification of electrodes. Electrodes are classified into different types depending on what kind of combination we have. We can have metal ion electrode, where the metal, let's say for example zinc, will be dipped in ZnSO4 solution, that is electrolyte of its own. We can have a second type of electrode where, example like gas electrode, or we can call this as non-metal ion electrode. For example, like chlorine gas, for the electrical contact we'll use platinum that will be in contact with the chloride ions, for example like HCl if we take the aqueous. Then we have third one, that's sparingly soluble salt electrode, where there will be some metal, let's say for example like mercury. For electrical contact will provide platinum because mercury is in liquid state. It will be in contact with its salt like Hg2Cl2, but it's sparingly soluble. Hence, we'll take one more electrolyte which is containing the anions. For example, the chlorine ions are present here. And the fourth type of electrode, which is nothing but redox electrode. Now, in case of redox electrode, for example, like Fe2 plus ions in contact with Fe3 plus ions, for the electrical contact we use platinum. Now in case of the cell presentations, we can use this particular different electrodes for the combination. So single vertical line, that is indicating the boundary between the metal ions and its electrolyte. So if I have to combine the two things, for example zinc solid in contact with Zn2 plus solution. So this is indicating the zinc is in contact with its own ions. You can provide the concentration of this particular solution. Double line will indicate the separate or the salt bridge. Let's say copper 2 plus ions are in contact with the copper electrolyte. So the electrode which is present on the left hand side, it's presenting the anode where the oxidation will take place, and the electrode which is present on the right hand side, it's the cathode where the reduction will take place. So these are different terms, or these are the different criteria you have to use. Now from this I can understand zinc is undergoing the oxidation and copper is undergoing the reduction processes. The next part is important for the MCQ point of view. That's the Nernst equation. We should remember. First of all, for the standard thing, E0 cell will be equals to E0 cathode minus E0 anode, provided they have given you the reduction potentials. Also, the EMF of the cell will be equals to E0 cell minus 0.0591 upon N log to the base 10, the oxidized state of that substance upon the reduced state. Okay, so this is something we have to use. For example, metal, let's say solid, is undergoing the oxidation. It's losing n number of electrons. We'll get M by losing n number of electrons. So this E will be equals to E0 cell minus 0.0591 is losing n electrons log to the base 10. This is oxidized state, so concentration of Mn plus upon concentration of M. But here we can see the M is in solid state, so its concentration can be taken as unity. So it's nothing but E0 cell minus 0.0591 upon N log to the base 10 M N plus concentration. We can also relate this to the Gibbs energy. Delta G will be equals to minus N E cell into F, that's Faraday's constant. Also delta G0 is equals to minus N E0 cell into F. So we can use these two formulas for relating to the Gibbs energy. Now there are two different type of the electrodes. One is the indicator electrode, whose potential is totally depend on the concentration of the particular ion which are present in the solution. While in case of reference electrode, the electrodes which are arbitrarily chosen and the potentials are fixed, we call them as reference electrode. Now in case of reference electrode, we have to remember two examples. First is SHE, standard hydrogen electrode. It's a primary reference electrode. That primary, that means this particular electrode is very difficult to set up and you have to determine its potential by setup of a certain equipment. Representation of this cell is done by H plus aqueous having 1 molar concentration in contact with the hydrogen gas having 1 atmospheric pressure, this is in gaseous state, in contact with the platinum. You can write the anodic reaction, that's oxidation reaction, half H2 gaseous state giving H plus aqueous plus electron. Opposite reaction if you connect this as a cathode. This potential of this is generally taken as 0. The standard EMF of this reaction is taken as 0. Also the calomel electrode, that's also one of the important reaction. In case of calomel, calomel cell is called as a secondary reference electrode because its potential is generally determined using standard SHE. It's metal sparingly soluble salt electrode presented by KCl, which is aqueous in contact with He2Cl2 solid in contact with mercury, which is in liquid state for the electric contact provided platinum. Now the concentration of KCl will decide the reduction potential of this particular calomel electrode. For the 0.1 normal solution, generally it is found to be 0.333. For the 1 normal solution, it is found to be 0.28, and when it is saturated, it is found to be 0.242. So these values are fixed for the calomel electrode. EMF series is nothing but the elements are arranged in the form of the electrode in the decreasing order of their standard reduction potentials. Hydrogen has a standard potential 0, so it's generally kept in between. Elements with the positive standard potentials are placed above and decreasing, so remaining are below. So we have to remember the EMF series has different application, including the spontaneity of the reaction can be checked. Spontaneity can be calculated if the E cell, if you get it positive, the reaction is spontaneous in nature. Also, in order to predict the oxidizing and reducing agent, the elements which are present above the hydrogen, they have the positive electrode potential. They are all good powerful oxidizing agents. While which are below hydrogen, they are good reducing agents. So these are the properties which we can use as application for the different EMF series. Whether also we can understand whether the metal can displace the hydrogen or not. So remember, the one which are present below hydrogen, they can displace hydrogen from aqueous solution, and this cannot displace the hydrogen from the aqueous solution, the metals which are present above hydrogen in electrochemical series. Now type of the galvanic cell, there are two types. Primary cell, it is the electrochemical cell in which the electrical current is generated within the cell itself. For example, we can remember the Daniell cell. The Daniell cell where the zinc is made as an anode in contact with the ZnSO4 solution, aqueous, in contact with the copper sulfate, with the copper is made up as the cathode. Potential of this Daniell cell E is found to be 1.1 volt. Secondary cell is an electrochemical cell in which the electrical current is not generated within the cell, but it is previously stored from the external source during the charging. So we can remember example of the storage. They are kind of like a storage cell, like a lead accumulator. So in case of lead accumulator, remember it's a charging discharging process. So during the charging process, this particular cell is made by Pb in contact with PbSO4. So this is made as an anode in contact with H2SO4 solution, which is generally 38% weight by weight percent is taken, in contact with PbSO4, which is solid, PbO2, which is made as a cathode, and in contact with Pb. So charging discharging processes of the lead accumulator is to be revised. So there are two types, primary and the secondary cell of the type of the galvanic cell. Fuel cell is very important with respect to the generation of the electricity and the water also. So here what we do is hydrogen is bubbled through its H plus aqueous solution containing NaOH, little bit of basic media, contact with OH minus, and O2, which is at the graphite. Both these electrodes are made up of the graphites. So this is negative and this is the positive electrode. So here what happens at the anode, that is hydrogen is bubbled. So the hydrogen in this aqueous media is converted into water by loss of electrons, while at the cathode oxygen in the water gains electrons to give OH minus ion. So this is overall process. If I talk, it's twice of H2 plus O2 generating the water along with the EMF of cell, which is generated. It's 1.299 volt. So this much of current is produced during this reaction. The last part that we'll be revising is a corrosion, which is a process of the tearing or wearing away, the gradual decay of the destruction of the metals when it is exposed to the atmosphere, especially if it is a moist air or something. Corrosion of the iron is one of the important example where iron undergoes the oxidation process with the loss of electrons. So some of the surfaces of iron acts like the anodic surface in presence of moisture. Now water in acidic media will dissociate into H plus and OH minus. This particular H plus and OH minus, this is generating the oxygen or water in this case. So twice of H plus plus half of O2 from the atmosphere will gain electrons, twice of electron to generate the water. So this Fe is then turning 2 plus, will further turn to the Fe3 plus, and this Fe3 plus will turn to Fe2O3. The hydrated form of this particular Fe2O3 is called as the rust. This can be avoided, factors that is corrosion can be avoided by alloying of metals, polishing the surfaces, production of the insoluble oxide coatings, electroplating, metal spraying, galvanizing, removal of string. So with the help of that we can remove the rusting or we can avoid the corrosion processes.